Okay, so in summary, the electric potential energy, the change in electric potential energy is equal minus the work done by the electric force equal the work done by the applied force. Okay, this is important concept that you have to remember and memorize, and you know how to use it. Now let's move to the second part, which is electric potential. Okay, and there's a definition for the electric potential. Okay, so the electric potential, it is defined as the electric, or the work done per unit charge. Okay, so imagine you have this again plus Q here, and you are bringing this charge from infinity to this point. Okay, that would be, and the distance between them is r. So how much is work we applied? What was the applied work? If you remember, it is K Q over r, and this is U. Okay, and so the potential V, this is the potential. That's the electric potential. At this point, I'm going to call this point P. Forget about, okay? So the point P, this is the potential produced by this charge here, because I'm bringing this is fixed, and I'm bringing this charge from infinity to this point, okay? It's U is equal over Q, the charge which is moving here to this point. So if you take this U here, KQ over, it gives you this equation here, okay? That's the potential, electric potential due to this point charge at this point P, okay? KQ over R, okay? And you notice here, very important, that this is that's the potential, okay? That's what I'm looking for. You notice that this potential, first of all, is a scalar. It can be positive if Q is positive, and it can be negative if Q is negative, okay? The potential has nothing to do with this charge plus Q, because when you divide by the charge Q, it disappears from this equation here. So it has only to do with the charge Q, which is producing this potential here, okay? All right? So that charge Q here, I'm going to draw it again here, plus Q. At this point, P, it produces two things actually. It produces an electric field, which is in this direction. I call it E. And I hope you remember what is the magnitude of the electric field is KQ over R squared. That's the magnitude at this point, where R is what? The distance between the charge and the point. And it produces also a potential at this point P, equal K Q over R, again the distance, okay? So this charge plus Q, any point charge, produce around it an electric field and a potential, okay? And that potential, as we move closer to the charge, R becomes small, potential increases. As we go away from the charge, R becomes large and the potential decreases, okay? Very important. That's now, since we defined that the potential is equal, the electric potential is the work done, or the potential energy per unit charge, I can do like this. The change in potential is equal the change in potential energy divided by the charge Q, which is moving, okay? The charge Q. That's a definition of the change in potential energy. Now, and I have a very important equation, the relationship between the change in potential energy and the change in potential, electric potential. Very important equation here. So the Q, the charge Q is actually, I can do something like this. Imagine you have an electric field here, okay? And my electric charge is moving. There's an electric charge here, Q, small q, this one, a positive charge here, okay, is moving from this initial position to the final position here. So there will be a change in potential energy to go from here, and there will be a change in potential to go from here to here, okay? So there is, here is V initial, here is what? V final, and here there is U initial, and there is U final also, and both of them are related through this equation here. Okay, delta U is Q delta V, okay? That's very important equation. It's a very important equation. Let me now do something here to show you exactly what is happening. It's very important to understand this point, my son. Okay, let me just give you the units of the potential since we are here. It's U over Q, so it's joules over Coulomb. Okay, and joules over Coulomb, I call it volt. Okay, it's volt. That's the units for V, with electric potential. It's volt. Okay, the SI units is volt. Now, let me go back to this figure here. Let me go back to this important figure here. The electric field is in this direction. And it's important to understand this, my son. My charge plus Q is moving from here to here, okay? Because of there's a force here. Well, don't forget, there's an electric force here which is moving it. It doesn't move by itself. It moves due to this force, electric force, which is that electric force is due to the electric field here, okay? And because the charge is positive, the force and the field are in the same direction, okay? So I have here, at this point, I have a potential V initial. At this point, I have a potential V final. I have here a U initial, and I have U final here, and they are related through this equation here. So delta U is the charge times what? Times delta V. And this is equal to minus the work of the electric field. We know this, huh? Delta U is minus the work of the electric field. Now, according to you, this is the displacement, is in this direction, that's ds. And the force, when the force and ds are in the same direction, okay, what do you think about the work? The work will be what? Will be positive. So the work done by electric force in this situation here is positive. And there's a minus sign here. Okay? There's a minus sign. So delta U is what? Delta U will be negative, okay? Delta U will be negative. And this is a positive charge, all right? It's a positive charge. So delta V will be also negative. Very important. Very important. Very important. What can we say here? A positive charge moves toward lower potential. Lower electric potential. Electric potential. Because according to this figure here, V here is less than V here. And the positive charge moves toward the lower potential. Okay? Lower potential. And I hope you understand that the potential here is less than here, less than here, less than here. As you move with the electric field, the potential decreases. Okay? Very important concept, my son, to understand this point. Okay? Now, so I have this important equation here, very important. I have this important equation here about the potential due to a point charge at the distance r, is kq over r, and I can also look at something else now. So I know that delta U is q delta V. This is very important concept. So here I can find that delta V is delta U over Q, right? But delta U is minus the work of the electric field over Q. All these things you should know them, my son, okay? And the work done by electric field is integral of Fe times what? ds, okay? ds. Between what and what? Between I and F. I and F. What is the angle here between ds and F? It's 0, so the cosine 0 will give me 1. So I can remove now those things in the arrows, okay? So delta V, the change in potential between this point and this point, which is V final minus V initial, and we know from here it's negative, okay? Potential here is less than potential here. Please remember this. You look at the direction of electric field. If I reverse the electric field in this direction, the potential here will be less than the potential here, okay? So as we move in with the electric field, the potential should decrease. Okay, very important. So minus, okay, so I have to divide by Q here. There's a Q here, a charge Q. So what is Fe? Fe was written before is, so I integrate between I and F. Fe is Q times E. Q times E, right? ds over Q. So what do you think about this Q? This is the same charge, by the way. So delta V in this case, very important equation here. I'm writing here in, I'm going to write it in red because it is very important. The change in potential between these 2 points, delta V, which is V final minus V initial, is equal minus integral between I and F of E. I can leave this, it doesn't matter. Here it is a straight, here they are parallel, but in general, so EDS, in general, okay? Sorry, yeah, EDS, okay? That's the change in potential energy. Very important equation here, okay? Very important equation. The change in potential energy can be given by this equation here. You notice that it depends only on the electric field and your displacement. It doesn't depend on the charge. The charge has nothing to do with it. Yes, of course. The charge, which is moving here, has nothing to do with the potential. This potential is created by the electric field. You can see it here, huh? Okay? You can see it here. So it depends only on E. And of course, your displacement, okay? Your displacement, how you are moving, or how are we moving in this electric field, okay? ds is important there also. So these are important things. I'm talking about electric potential. Is defined as the work done by unit charge. This is the work applied. I gave you the example here. It is work applied is equal to the same thing as U. So you take U, you divide by unit charge, by the charge Q, which we are moving, and you get the potential at this point. At this point here, P, potential at point P, due to this charge here, KQ over R. So the only thing you have to know is that there is a charge here, the charge itself, and R is the distance between the charge and the point where you want to find the potential. The potential can be positive, can be negative, depending on the sign of the charge. Okay? And it is involved. And also, this important concept here, that the change in potential depends only on the electric field. Thank you. Okay, let me show you something now. Imagine you have an electric field like this, in this direction, to the right. You can know by looking at the arrow here, and it is uniform. Not always, it doesn't have to be uniform, but again, for simplicity here, to make things simple. And I hope, if I tell you this point here, as a potential initial, potential VI, and this point as a potential VF, you can tell me that, I hope you can tell me that this point has a lower potential. This is lower potential. But lower than that, than what? Than this guy here. This guy has lower potential than this point, and this point that has higher potential than the other one. Higher potential. Okay? So as you move in this direction, as you go in this direction, you go to lower potential. Very important, huh? As you go in this direction, you go to higher potential. Let me give you an example. So, if the potential here is 50 volts, here it will be 60 or 70 or 80 or 90, higher than this point here. Huh? If the potential here is 100 volt, the potential should be 90, 60, 40, and so on, lower than this potential here. Very important, okay? Now, let's go to this important equation that we have seen before. It says that delta V minus integral of E dot ds. Okay, that's important. And let us move from this point, I. See, there's a point, there's nothing there, there's no charge. Huh? This electric potential is created by the electric field. There's no charge here, okay? And I go to this point through this, through here, like this. Okay? I'm going. This is my now. Since E is uniform, I can write it like this: minus E. I take it out of the integration, and dot D, the displacement. Okay, displacement. I call this one D here. Okay, this is my D. displacement, because integral of ds will give me the displacement d between I and f, and of course this will be minus e d cosine of theta. Okay, so delta v for uniform electric field, delta v is minus e d cosine theta. Very important. Okay, this is if E is uniform, we have to write here E uniform so that you don't make a mistake, because we are taking E outside the integration here. Okay, so it has to be uniform. So as you move from this point to this point, the angle between E and D is 0. Okay, so how much is delta V for this case? Case number 1. Here, delta V is 1 minus ED, and this will be negative. And you were expecting this, because this is let me write down before I write negative. This is VF minus VI, and this is negative. It means that the potential, the electric potential at this point is less than electric potential at this point. This is 50 and this is 100. So 50 minus 100 will give you a negative number. You have to understand this point. This is clear. We said it many times. It's here and it is here again. Okay? Now, imagine now I'm going to move from this point, initial, to this point here, final. Okay? And this is my displacement. This is case number 2. Let's see how much will be delta V in this case. And you are expecting, of course, that it will be minus E D cosine what? 180. And cosine 180 is what? Is minus 1. With minus 1, it gives you what? E times D, and this is positive. Of course, the potential here, the potential at this point is higher than the potential here. Higher potential, lower potential. You can see it from this equation. It's clearly now. Let's go now, case number 3. We go from this point to this point here. This is my D, okay? My D. I'm going from I to F. Okay, this is case number 3 here. Case number 3. Case number 1 was here. Case number 2 was here. And this number, okay, case number 3. How much is delta V in this case? Case number 3. I put here 1. I put here 2. And this is 3. So in this case number 3, my delta V will be E minus ED cosine 90 degrees. That's the angle between my displacement and the electric field. You can see it here. And this is 0. It means V final equal V initial, which is what? It's a constant. Okay? Which is a constant. Now, let me draw a figure here. So I have the electric field lines. Okay? And I have these planes. They call them planes. They have a constant potential. Okay, I hope you are seeing these planes. These are planes. They call them planes equipotentials. These planes, which are perpendicular to the electric field, planes are perpendicular. They have the potential here. V is constant. Okay. Again, V here is constant. But the value of V here and V here are not the same, but V in this plane is constant, okay? V again here is what? Is constant. We call these planes, we call them equipotentials, okay? We call them equipotentials because they have the same potential on the plane, okay? Equipotential. The potential on this plane, if it is 20 volts here, 20 volts everywhere, 20 volts, okay? And here it will be less, of course, maybe 10 volts here on this plane. Everywhere on this plane, it's 10 volts. So we call this one equipotential surfaces, okay? You can see them. They are surfaces, okay? For the case where the electric field is, this is the electric field, by the way, yeah? The red arrows here represent the electric field lines. So the electric field, the equipotential are always, let's write down here, the equipotentials are always perpendicular, I hope you understand this notation here, perpendicular to the electric field lines, okay? Here, the electric field lines are parallel lines, so the equipotential have to be parallel planes or surfaces, or planes. Equipotential plane, we can say planes, or surfaces, the same thing, okay? They are planes or surfaces. Now, be careful along that plane, the potential is constant, okay? Now let me show you something else now. Okay, let's move on in these concepts, important concepts. You have to be careful, my son. These are the concept of electric potential is very important. Okay, so let's move on now. If we take now an equipotential, let's take an equipotential and discuss. So this is my equipotential. Let me draw it like this. Okay. Okay, my equipotential, and I start from here and I go here, and I'm going to move. Okay, a charge Q. So I have a charge Q, positive charge. I'm moving it from here through this path, like this, moving it. This is the motion. Okay. So how much work? Network. What is my network? W net by done. Let's say by me. Okay, to move it from I to F. And the work net is equal the change in what? Potential energy. This is applied. This is applied. This is applied. Let's say this is applied by me. I'm moving the charge. Okay, I'm moving the charge, and this is equal to delta U is equal QH delta V. So it will be Q V final minus V initial. But you know that the potential here and here are the same because this is an equipotential. We said that equipotential along an equipotential. On the equipotential, the potential is constant. We said that V is constant. So how much is this? This is 0. Okay, this is 0. So the work is 0. So the net work done to move a particle, a charged particle from an equipotential back to the same equipotential, the work done will be 0. It's a very important concept. The net work done. So there will be a positive work, a negative work, and so on. But the net work will be 0 for that motion. Okay. Now let me show you the equipotential when you have a positive point charge. So I have a point charge plus Q, and you know if you have a point charge plus Q like this plus Q, and you know that the electric field lines in this case are radially outward. You know that very well. They are radially outward. And let's now draw the equipotentials. And we said that the equipotentials are always perpendicular to the electric field lines. So if I want to draw the equipotentials, I have to draw them in this manner. Okay? They have to be like this so that they are perpendicular to the electric field lines, and you can imagine what are these equipotential. They are not surfaces or planes like in this case. They are spheres. Okay, so another equipotential will be this one here. It will be another sphere. Okay, so these are the equipotential for a point charge, a positive point charge. Even if the charge was negative, the electric field will be inward radially, and the equipotential will be also spheres. So equipotentials are sphere, concentric spheres. Concentric means they have the same center, and the center will be the charge itself. Concentric spheres. Okay, very important concept. But of course, you should know, my son, by now, that the potential at this point and this point are not the same. But the potential here and here and here on the surface, on the same surface, it's constant. But the potential here, if I call this one V1, I call this one V2. Let me ask you, my son, which one is higher? We said as we move with the electric field, we go to lower potentials. And so you can tell me, I am moving with the electric field. As I move with electric field, I go from V1 to V2. So I expect V2 to be lower than V1. Yes, V2 will be less than V1. And if you remember very well, we wrote the potential for a point charge. It was K, Q over R. Can you tell me why V2 is less than V1 from this equation here? Because, of course, at V2, the R is bigger than at V1, and therefore, we have bigger R, smaller potential. Everything makes sense, okay? Things have to be together like this. There will be no confusion in this case. Thank you.